the temperature scale and ideal gas law. And then we're going to do the expansion of materials, volume expansion, linear expansion, and area expansion. So the other day we talked about the Kelvin and Celsius scale, and I kind of connected it to the idea of radiation and the black body radiation and Wiener's law. And then the other one is the Fahrenheit to Celsius scale. Fahrenheit is 950 Celsius plus 32. So that means the Celsius of 0 is equivalent to Fahrenheit of 32. And Celsius of 100 is equivalent to Fahrenheit of 212. So this is the freezing point of water. Freezing point. This one is the boiling point. And then the Celsius 37, remember that was the body temperature. That one would be Fahrenheit of 98.6. This is human body temperature. And then Celsius of 27 is would be the sort of the regular room temperature. So that's Kelvin of 300. It's a good round number. So then what would that be? We put 27 here. That'd be about 81. Not quite 81, but something like 81. So you have to put here 27, then you get Fahrenheit 81. So you can say this is room temperature. And then there's one temperature for which the Celsius and the Fahrenheit actually are equal to each other. So as you go down in temperature, see 100 and this is 212, is how different they are from each other. The Fahrenheit is 112 degrees bigger. As the Celsius goes to 0, the Fahrenheit is 32. So notice they got close to each other, right? So if you keep going lower, there's a particular degree where the Celsius and the Fahrenheit are equal. So to solve for that, you can set F equal to C, which equals 9/5 C plus 32. You say, what does that mean? Well, at that point, they're just the graphs of the two cross each other. And so then you're going to have your C minus 9/5 C plus 32. So then you subtract 5/5 minus 4/5 C is 32. C is equal to 32, and then times minus 5/4. 8. C is negative 40. So when the Celsius is negative 40, the Fahrenheit is also negative 40. Okay. So by the time you go down to, this keeps getting more negative. See, negative, for example, negative 10, you're going to have Fahrenheit is positive. The other one to calculate is when the Fahrenheit finally reaches 0, what is Celsius? Right? When the Fahrenheit is 0, that's really cold, right? What is Celsius going to be? So then you just solve for your 0, 9/5 Celsius plus 32. 9/5 Celsius is negative 32. And then Celsius is going to be negative 160 over 9. Negative 1 with 70. 9 goes into 78 times.
6.
Huh? 170, 9 goes into 76 times.
7.
Oh, 7 times, yeah, 7 times. 63 with 7 left over, right? So then 70, so it's going to be repeating 7s. Okay, so when the Fahrenheit is 0, Celsius is negative 17, right? So then when the Celsius keeps getting more negative, they're starting to approach each other. When Celsius gets to negative 30, Fahrenheit is probably something like negative 25. And then finally, when the Celsius reaches negative 40, Fahrenheit reaches negative 40. Okay, then what happens when the Celsius is cooler than that? When the Celsius is, let's say, negative 60, what would be the Fahrenheit? Well, then you just put it into this equation. That's 12. 12 times 9, that's negative 108, right? Plus 32, negative 76. This is Fahrenheit. So negative 60 Celsius is negative 76 Fahrenheit. So what happened now? Now the Fahrenheit is below the Celsius. So it's larger. It's larger in the sense that its magnitude is larger. You see? So anything cooler than negative 40 Celsius, the Fahrenheit is going to be lower down. You see? Lower down on the number line. So if you kind of think of a scale like this is the Celsius and this is the Fahrenheit. At negative 40, they match. So anything as this one goes up, right, that means this one is going to be higher. So like that, like that, like that, like that, like that, like that. So by the time you get to 0 Celsius, you're at 32 Fahrenheit. And by the time you get to 100 Celsius, you're all the way to 212. You see? But then negative 40 they match, but then anything lower than negative 40, like negative 60, now the Fahrenheit is negative 76. Right? And then when you go down to absolute zero, negative 273.15 Celsius, you're going to be all the way down here or something, right? Absolute zero is going to be like negative 400 or 500 Fahrenheit. So then you put this into here, 273, 9/5 of that. Okay. So, 273.45 times.
Because that's already in the shooting, right?
Negative 459.67. So all I did is I put this here, calculated it, so you see. That means that's even bigger difference than the boiling point. The boiling point was 102 and 212, whereas this is negative 273 and negative 459. Okay, cool. So now let's see the connection of this to the ideal gas law. The ideal gas law is kind of a conglomeration of years of thought and experimentation that we proved slowly over time that pressure is inversely proportional to volume, and pressure is linearly proportional to temperature of a gas. So we've got the two major forms of the ideal gas law. PV is nRT, and the PV is big NKT. I know in chemistry they probably focus more on the nRT version, whereas here we focus on, well, kind of both, you know. So N would be the number of moles. R would be the universal gas constant. Okay, and then the universal gas constant is 0.02. Let's see here. So we can get the right numbers. Okay, so let's see here. Okay, so we got several possible units. 0.0821 liter atmosphere per mole Kelvin. So that's the version you probably have used a lot in chemistry. 0.0821 liter atmosphere per mole Kelvin. So if you're going to use that version of the ideal gas law, then the pressure is going to come in units of atmospheres, and the volume is going to come in units of liters, right? So that pressure is in atmospheres, and volume is in liters. But then if you use this version, 8.3145, joule per mole Kelvin. So then what's the units of pressure? Pressure would be then the units pascals, right? Pascals. And volume would be meter cubed. And then the mole would cancel the mole, and the Kelvin would cancel the Kelvin, right? So how does it end up being a joule? So in other words, pressure times volume stated as a Pascal times volume, can we show that that's actually a joule, right? So Pascal times volume. Remember, Pascal was pressure, which was Newton per meter squared. Newton times meter, which is joules. See, this form of the universal gas constant kind of hides the fact that PV is a unit of joules, is a unit of energy. You don't really see that, you don't notice it. It's just liter atmosphere, which is why this is the better version, you know? Because then you say, oh, PV is actually has to do with the work that the gas did, you see? And it's more obvious that it's units of energy. What other units are there? 8.2057 meter cubed atmosphere over mole Kelvin. I don't think we use that one too much. And then the other one, 62.3637 liters torr per mole Kelvin. It's not really used too much either. You convert it to units of, remember 761 torr is what? 760 millimeters mercury? Right, so I don't think we're going to use that one too much, unless we have to for a particular problem. But those two are the more common one. Then the N, if you use this version, big N is the number of particles. K is Boltzmann's constant. Boltzmann founded the whole field of statistical mechanics. Which is why thermodynamics, which is what we're studying now, sometimes is also called statistical mechanics. So the statistical interpretation of gases and what they are doing on the molecular level. So Boltzmann found that, and then we honored him by naming this constant after him. And I think he had some kind of depression or something. He committed suicide very early in his life. But he was famous for that. So then Boltzmann's constant would be what? 1.38064852 times 10 to the minus 23. Okay, and then meter squared kilogram per second squared Kelvin, but can we do that in terms of a joule? Let's see, if this is units of joule, right? And this is would have to be joule per Kelvin, right? And then particles, yeah, you could probably say joule per particles per Kelvin. But I don't think we need to put particles. We just put joule per Kelvin. So in other words, all this is just a joule, right? Kilogram meter squared over second squared. A Newton is a kilogram meter per second squared. Yeah, this is a joule. Yep, exactly. So that is a joule per Kelvin. See? Okay, then what's the connection between these two? Well, if these two are the same, that means NR needs to equal NK, right? Right? This is number of moles, this is gas constant, this is the number of particles. But we know that the number of particles is equal to number of moles times Avogadro's constant. So the number of particles is N times Avogadro's constant. So now we have Avogadro's constant. So all these things are all connected. And Avogadro's constant 6.022 times 10 to the 23, 1 over mole, right? Or you could say particles over mole. You see, because particle is not a unit, they just ignore the particle. So Na is 6.022, let's say, times 10 to the 23, 1 over mole. So does that make sense? Okay, so now, if that's true, N cancels N, the gas constant should be Na times K. So in other words, the gas constant and Boltzmann's constant and Na are all connected, right? So if you take the Avogadro's number times Boltzmann's constant, 1.38 times 10 to the minus 23, what should happen? That should cancel, right? So Boltzmann's constant is 10 to the minus 23, whereas Avogadro's number is 10 to the 23. That portion of it cancels itself. Then you get 6.022 times 1.38, and then that one, when you multiply, it should give you the gas constant. Let's see here. .38 times 6.022. .31, huh? Didn't come out exact. Probably we need more sig figs.
Would it be the joules per mole? Okay.
Huh? Oh, you mean the units? Yeah, the units should work out because this is 1 over mole and this is joule per Kelvin. Joule per Kelvin. Joule per Kelvin times 1 over mole, which is joule per Kelvin mole. You see? In other words, K, the units of the K are joule per Kelvin, and the units of this guy is 1 over mole. So then when you multiply, it's joule per mole per Kelvin, joule per mole Kelvin.
8.31, yeah.
Yeah, 8.31. And then the 4.5,
Yeah,
probably, yeah, it would have worked out maybe.
Pretty close.
So you see they're intertwined, those three versions. So it's kind of interesting that we could actually use the ideal gas law to actually prove that the temperature of absolute zero is negative 273. You know, so it's actually a cool experiment that we could do, and I have it in one of my videos. It's in the chapter 19 playlist.
Morning, guys.
Hey!
I apologize for